Micronutrients include the chemical compounds that fall into the categories of vitamins and minerals. The importance of micronutrients in sports nutrition is often overlooked by athletes due to the emphasis on macronutrients that pervades their readings and conversations on sports nutrition. The lack of interest in micronutrient consumption, combined with a diet that overemphasizes one macronutrient over the other two, may lead to deficiencies in daily intakes of key micronutrients. Chronic deficiencies may at a minimum negatively affect athletic performance, but could also lead to the development of diseases such as anemia and osteoporosis. The roles of various micronutrients in support of various metabolic processes will be discussed in this module, along with the recommended intakes of commonly deficient micronutrients in the athlete's diet. By the end of this module, you will be able to classify a vitamin as either water-soluble or fat-soluble, differentiate between macronutrients and micronutrients, provide examples of food groups supplying micronutrients, summarize specific physiologic functions of the micronutrients presented in this module, determine the ergogenic properties of the micronutrients presented in this module, and recognize the different names associated with the micronutrients presented in this module. The first three parts of Module 2 concern the three macronutrients commonly consumed in our diets. Protein, carbohydrates, and fats are the compounds that make up the majority of the food we eat and are required in large amounts on a daily basis to support ATP resynthesis, build cellular structures, and participate in various additional cellular processes. In contrast, the term micronutrient describes a chemical compound that is needed in very small quantities relative to the macronutrients, and typically is involved in supporting the metabolism of the macronutrients in some capacity. While there are only three macronutrients, numerous micronutrients have been identified. These compounds have been grouped into categories known as vitamins and minerals. Vitamins are organic compounds that aid in metabolic reactions or help neutralize reactive oxygen compounds by serving as an antioxidant. Vitamins play a large role in particular in supporting the numerous chemical reactions that make up the bioenergetic pathways discussed in Module 1.2. Minerals are inorganic compounds that can be found on the periodic table of elements and that also aid in various metabolic reactions and serve as antioxidants in our cells. Since both vitamins and minerals support bioenergetics pathways, it has been believed that athletes require larger amounts of these compounds in our diet to support the increased demand for ATP that occurs with exercise. However, ergogenic benefits of consuming micronutrients above the recommended daily allowance set by nutrition scientists have not been identified. Therefore, as a whole, athletes do not need to be advised to consume excess amounts of the micronutrients. Perhaps more important is the prevention of micronutrient deficiencies that may arise in athletes attempting to lose weight or who focus on one macronutrient at the expense of the other two. Vitamins can be further subdivided into categories based on the substance in which they are soluble. Water-soluble vitamins are transported through the blood and are not stored for any significant length of time in a cell. Therefore, any consumption of water-soluble vitamins above amounts needed to support metabolic reactions occurring shortly after their absorption will cause the unused water-soluble vitamins to be excreted in urine. The water-soluble vitamins include the B vitamins, folate, biotin, and vitamin C. Fat-soluble vitamins bind to chylomicron proteins in the blood upon absorption and are able to be stored in adipose tissue for extended periods of time. The fat-soluble vitamins include vitamin A, vitamin D, vitamin E, and vitamin K. Each of these vitamins may create unwanted symptoms if consumed in excessive amounts over several days or weeks due to a limited capacity for storage. Vitamin B1 is more commonly known as thiamine. Thiamine may be present in its free form in the blood, or it may be bound to different numbers of phosphate groups to form thiamine monophosphate, thiamine triphosphate, or thiamine pyrophosphate. Thiamine triphosphate aids in the propagation of action potentials in neurons by activating the ion channels that allow for the flow of sodium or calcium down concentration gradients to cause depolarization. Thiamine triphosphate is also a required coenzyme for several Krebs cycle reactions in support of ATP resynthesis through cellular respiration. Thiamine pyrophosphate also serves as a coenzyme for some Krebs cycle reactions, and thus thiamine supplementation has been theorized to have an ergogenic effect, particularly in endurance exercise. However, since most foods are fortified with thiamine, deficiencies in this micronutrient are uncommon, and most studies involving human subjects do not find any ergogenic benefits to consumption of thiamine above the RDA. Therefore, supplementation is not warranted, and instead athletes should be educated on the food sources of thiamine, including enriched or fortified grain products such as breads or cereals. Vitamin B2 is commonly known as riboflavin. Recall from Module 1.2 that the primary purpose of the Krebs cycle is to produce the electron carriers NADH and FADH. FADH is short for flavin adenine dinucleotide, and therefore riboflavin provides an important building block for FAD. While riboflavin plays an important role in the oxidative metabolism of our macronutrients for ATP, it also plays a role in managing unwanted reactive oxygen species within a cell. Riboflavin is a component of the enzyme glutathione reductase that catalyzes the reduction of glutathione. Reduced glutathione can then be used to donate electrons to hydrogen peroxide, which is considered an oxidant. Additionally, riboflavin is part of the enzyme xanthine oxidase, which is used to catalyze the production of uric acid. Uric acid provides a more potent antioxidant in blood plasma than any other compound. As with thiamine, deficiencies in riboflavin are uncommon, and studies involving human subjects have not demonstrated any ergogenic benefit of riboflavin supplementation. Athletes should be encouraged to obtain the RDA of riboflavin by including organ meats, milk, fortified breads, and fortified cereals in their diets. Vitamin B3 is commonly known as niacin. A byproduct of both glycolysis and the Krebs cycle is NADH. NADH is short for nicotinamide adenine dinucleotide, and niacin is an important component in the production of this electron carrier. While NADH is a potent electron carrier in cellular respiration, it is also able to donate electrons in many other chemical processes in the cell, and along with the phosphorylated version of this molecule, NADP, is required in over 200 enzymes involved in the catabolism of macronutrients, along with the synthesis of fatty acids and cholesterol. As with thiamine and riboflavin, human subject studies have not found any ergogenic benefits to consumption of niacin above the RDA. Niacin can be obtained from consumption of meat, fish, poultry, and fortified grains. Vitamin B5 is known as pantothenic acid. Recall that the first step in the Krebs cycle involves the 2-carbon compound acetyl-CoA. The acetyl portion is the 2-carbon compound that can be derived from pyruvate via glycolysis or through fatty acid via beta oxidation. The coenzyme A portion includes pantothenic acid. Therefore, like thiamine, riboflavin, niacin, and pantothenic acid all serve important roles in supporting the Krebs cycle and the mitochondria, where the Krebs cycle takes place within the cell. Pantothenic acid can be obtained by consuming chicken, beef, potatoes, oats, egg yolks, cereals, or broccoli. Vitamin B6 may take several forms in the cell. It may exist as pyridoxal, pyridoxine, pyridoxamine, pyridoxal phosphate, or PLP, pyridoxine phosphate, or pyridoxamine phosphate. Pyridoxal phosphate, or PLP, is the most relevant form for sports nutrition due to its role in glucose metabolism. PLP serves as a coenzyme for glycogen phosphorylase and supports the reaction that removes an individual glucose molecule from a glycogen molecule. PLP serves as a coenzyme for the reactions that convert the branched-chain amino acids into glucose via gluconeogenesis. Finally, PLP is a coenzyme for the production of a number of neurotransmitters, including serotonin, dopamine, norepinephrine, and gamma-aminobutyric acid. Neurotransmitters are the chemicals nerve cells use to communicate with each other. Vitamin B6 is prevalent in fish, organ meats, potatoes, fruits, and fortified grain products. Folate is a vitamin that serves as a cofactor in chemical reactions that transfer 1-carbon units to and from other compounds. These reactions are relevant to the metabolism of both nucleic acids and amino acids, and folate is a micronutrient emphasized during pregnancy to ensure adequate development of the fetus. However, in sports nutrition, no ergogenic effects of folate supplementation on athletic performance have been noted, even under conditions where folate deficiencies are corrected. Folate can be found in dark leafy vegetables, fortified grains, and whole grain products. Biotin is also known as vitamin H, but it is labeled as biotin on food labels. It is an essential vitamin because it cannot be produced in the body, and it is known as a cofactor to 4 enzymes. It binds to acetyl-CoA carboxylase to complete the binding of bicarbonate to acetyl-CoA. This is an intermediate step to the conversion of acetyl-CoA to malonyl-CoA, which is a compound required for the synthesis of fatty acids. It binds with pyruvate carboxylase to aid in the process of gluconeogenesis. The third enzyme it aids is methylcrotoneal-CoA carboxylase, which supports leucine metabolism. Recall from Module 2.3 that leucine is the amino acid that stimulates muscle protein synthesis. Finally, biotin binds to propional-CoA carboxylase, which is an enzyme that supports the metabolism of various amino acids, odd-chain fatty acids, and cholesterol. No studies have been performed examining the ergogenic benefits of biotin on athletic performance. Biotin can be obtained from foods including liver, fruits, and meats. Like biotin, vitamin B12 must also be obtained from the diet. It is the largest of the vitamin compounds and even contains the mineral cobalt, providing vitamin B12 with its alternative name of cobalamin. It functions as a component of two molecules in the cells. Methylcobalamin is a compound involved in converting homocysteine to methionine. Homocysteine is a form of the amino acid cysteine that is not considered one of the 21 amino acids derived from the proteins we eat. High levels of homocysteine in the blood are considered atherogenic due to their propensity for promoting endothelial injuries in vessels that stimulate plaque formation. Therefore, having enough methylcobalamin in the blood to convert homocysteine to methionine may have important health implications. The other compound formed from cobalamin is 5-deoxyadenosylcobalamin, and it serves as a coenzyme for the production of succinyl-CoA, which is a Krebs cycle intermediate compound. While no ergogenic benefit to athletic performance has been found with consumption of vitamin B12 above the RDA, deficiencies in this vitamin should be avoided due to its role in cardiovascular health. Vitamin B12 is prominent in animal products like meat, fish, and poultry, but also may be fortified in grain products. Vitamin C is also known as ascorbic acid, but is present on food labels as vitamin C. It is another vitamin that must be obtained from the diet, and its importance became apparent during historic long sea voyages where the deficiency disease known as scurvy was prominent. Scurvy is a disease marked by the deterioration of collagen in the body. Collagen is a protein found in all of the connective tissues in the body, including ligaments, tendons, cartilage, menisci, and skin. Vitamin C is required for the production of collagen. Additionally, vitamin C is a component of the protein carnitine in cells. Carnitine serves to shuttle fatty acids from the cytosol of a cell to the mitochondria for metabolism via the Krebs cycle. Vitamin C can also reduce free radical compounds by providing an electron to them and serves as one of the most potent antioxidants available to the body. Due to its antioxidant properties, vitamin C has been studied extensively for its role in reducing the free radicals formed during exercise. Collectively, these studies indicate that vitamin C may improve the extent of muscle damage that occurs due to exercise. However, large doses of vitamin C have been found to be pro-oxidant and may worsen the muscle damaging effects of exercise. Therefore, the evidence does not support intake of vitamin C beyond the RDA. A tolerable upper intake for vitamin C has been established, and intakes beyond this limit of 2,000 milligrams per day may produce symptoms such as diarrhea, nausea, and stomach cramps. Common sources of vitamin C include citrus fruits, tomatoes, potatoes, strawberries, and spinach. Vitamin E is a fat-soluble vitamin referring to a group of antioxidant compounds known as tocopherols and tocotrienols. Vitamin E is a powerful antioxidant, with alpha-tocopherol being the most active form in our body. Numerous studies have examined the effects of vitamin E supplementation on muscle damage and have produced mixed results. Therefore, it cannot be stated with confidence that supplementation above the RDA for vitamin E will reduce oxidative damage from exercise and improve the recovery between exercise sessions. In addition, no studies on vitamin E have demonstrated improvements in actual exercise performance following supplementation. Therefore, supplementation with vitamin E above the RDA is not recommended. Vitamin E can be obtained by eating vegetable oils, nuts, meats, fruits, and vegetables. Vitamin A is a fat-soluble vitamin, referring to a group of antioxidant compounds known as retinol, retinal, or retinoic acid. As with vitamin E, no evidence has been found of increased exercise performance with vitamin A supplementation. Vitamin A is not as potent an antioxidant as vitamin C or E, so supplementation for the purpose of reducing oxidative damage from exercise is not warranted. Vitamin A can be obtained from dairy, fish, leafy vegetables, and dark-colored fruits. Vitamin D may take many forms, but cholecalciferol is the primary form used in the body. Vitamin D3 can be generated in the skin through exposure to UV light that converts 7-dehydrocholesterol to vitamin D3. Consumption of vitamin D in the diet is not necessary if ample exposure to sunlight is provided. However, there is growing evidence that athletes are deficient in vitamin D3, perhaps due to limitations in sun exposure. The implications for this deficiency are unclear, but at present no evidence suggests an ergogenic benefit to vitamin D3 supplementation. Vitamin D is present in fortified milk, fatty fish, and fortified cereals. Vitamin K serves as a coenzyme for vitamin K-dependent carboxylase, which catalyzes the carboxylation of glutamic acid to gamma-carboxyglutamic acid. This reaction is critical for aiding the binding of calcium to certain proteins. However, this process does not serve any apparent purpose with regard to athletic performance. Therefore, no studies have been performed on the ergogenic benefit of vitamin K, and supplementation beyond the RDA is not warranted. Sources of vitamin K include green vegetables, cabbage, plant oils, and margarine. There are many minerals that play a role in a variety of metabolic processes throughout the body. Within this module, we will focus only on those minerals that have been found to have an impact on the performance of athletes. Like vitamins, minerals are classified into subcategories. Macrominerals are those that are needed in large amounts on a daily basis. The daily needs of macrominerals range around 1 gram per day. In contrast, trace minerals are those that are needed in much smaller amounts, ranging from micrograms per day to around 100 milligrams per day. Calcium is the most abundant macromineral in our bodies and plays several vital roles related to exercise performance. It makes up a large portion of our bones, particularly the cortical bone portion, and provides rigidity and stiffness to these structures. Since muscles attach to bone to produce movements and joints, the maintenance of bone health through appropriate daily intake of calcium is vital for all athletes. Recall from Module 1.2 that calcium is also stored in the sarcoplasmic reticulum of our muscles and is released when an action potential propagates through a muscle. It then binds to troponin to expose the binding site of actin in order for myosin to form a crossbridge with actin. Maintaining calcium levels in our muscles and other cells that use calcium for metabolic processes takes priority over maintaining bone. Therefore, if calcium intake is chronically low, calcium will be removed from bone to ensure a steady supply for other tissues. While calcium is vital to many physiological processes, there is no evidence supporting an ergogenic benefit of consuming calcium in amounts greater than the RDA. Good dietary sources of calcium include dairy products and vegetables such as soybeans, broccoli, collards, kale, and okra. Chromium is a trace mineral that cannot be supplied from any storage source in the body and must be obtained from the diet. Two forms exist, but trivalent chromium, known as chromium-3, is the form used by the body. Chromium improves the function of insulin and therefore is important in the metabolism of glucose. Since insulin is also an anabolic hormone that can lead to increases in muscle protein synthesis, numerous studies have been conducted to determine if chromium supplementation above the RDA provides any improvement to body composition. Despite these studies and some early promising results, the majority of the evidence available does not support the use of chromium to alter body composition or improve exercise performance during training. Dietary sources of chromium include meats, poultry, fish, and fortified cereals. Iron is another trace mineral that has a vital supporting role in physiology that largely impacts exercise performance. Iron is a major component of the heme molecule that makes up the hemoglobin found in red blood cells. Oxygen from the alveoli in our lungs diffuses down its pressure gradient and into the capillaries, perfusing them where it will bind to the heme and red blood cell. Each hemoglobin molecule can carry 4 oxygen molecules, and there are 150 grams of hemoglobin per liter of blood in males and 130 grams of hemoglobin per liter of blood in females. Heme is also found in myoglobin, which is the oxygen transport molecule within a skeletal muscle. In addition to these two important uses of iron, hundreds of proteins and enzymes in the body incorporate iron as a cofactor, including the cytochrome proteins that line the inner mitochondrial membrane. These cytochrome proteins support the electron transport chain and the oxidative production of ATP. Peroxidase enzymes also contain heme and therefore iron. These enzymes help neutralize hydrogen peroxide, which is a reactive oxygen species discussed earlier in this module. Chronically low levels of iron intake limit the amount of heme that can be produced and therefore the amount of oxygen that can be carried in the blood. The condition of low iron levels in the body is known as anemia. Since iron consumed in the form of heme is absorbed more readily than free iron, meat is considered the best source of iron. Vegan and vegetarian athletes may require iron supplementation to make up for low iron levels in plant products. Good plant sources of iron include lentils, soybeans, quinoa, nuts, and seeds, and collards. Supplementing with iron above the RDA does not produce an ergogenic effect by boosting the amount of hemoglobin in the blood. However, iron depleted or anemic athletes can expect an ergogenic effect from supplemental iron as their iron levels normalize. In fact, an upper limit of 45 milligrams per day has been set for iron because excess iron in the body can lead to symptoms such as chronic fatigue, joint pain, abdominal pain, irregular heart rhythms, hair loss, and depression, among others. Magnesium is a macromineral that is involved in over 300 metabolic reactions throughout the body. Of the 25 grams of magnesium found in the body at any given time, 60% is found in bones and 27% is found in muscles. Magnesium is a physical component of bone, cell membranes, and chromosomes, and is involved as a cofactor in the metabolism of macronutrients and nucleic acids. In addition, the active transport of potassium and calcium across cell membranes against their concentration gradients requires magnesium, and the ATP that it is stored in our cells is typically stored bound to magnesium. Like iron, magnesium supplementation has been shown to have ergogenic effects on males and females with low magnesium values to begin with, but intakes above the RDA for individuals who have normal magnesium levels does not affect exercise performance nor body composition. Sources of magnesium include green leafy vegetables, nuts, meats, starches, and milk. Zinc is another trace mineral that is an important structural component of cell membranes and various proteins. More than 100 enzymes require zinc as a cofactor to function properly, and it plays a role in cell signaling, nerve conduction, and apoptosis. It is part of the antioxidant molecule copper-zinc superoxide dismutase, which neutralizes reactive oxygen species, particularly as they interact with cell membranes. Therefore, low zinc levels can limit the amount of this antioxidant and make cell membranes susceptible to the oxidative damage that occurs with exercise. Intakes above the RDA have not been shown to have an ergogenic benefit, and zinc is found readily in red meat and seafood products along with fortified cereals. Phosphorus consumed in the diet is primarily used to form phosphate molecules in the cell that play critical roles in biochemical pathways in every cell of the body. Phosphate molecules are commonly added to other molecules to add energy via the phosphate bond and tag the molecules for various subsequent chemical reactions. The majority of phosphorus consumed is stored in bone by binding with calcium to form the calcium phosphate that makes up the rigid cortical bone. Even though it is a component of ATP and creatine phosphate, consumption of phosphorus above the RDA does not lead to increased amounts of either molecule in skeletal muscles, and intakes above the RDA are not warranted for athletic performance. Phosphorus is a common component of food and can be found in dairy products, meats, eggs, breads, and cereals. In summary, the appropriate strategy for an athlete to take regarding micronutrients is to consume a well-balanced diet that incorporates a variety of food choices in order to maintain the RDA of each micronutrient per day. Multivitamin supplements are not necessary if a balanced diet plan is followed. However, athletes who are not willing to do so may benefit from taking a multivitamin. It is important to note that micronutrient intakes above the RDA for any of the micronutrients will not produce an ergogenic effect on exercise performance. The only potential exceptions to this statement are vitamins C and E. Intakes above the RDA for these vitamins may increase the antioxidant capacity of skeletal muscle, but care should be taken not to exceed the upper limit for either. While iron has been shown to have an ergogenic effect, Recall that this was only for those athletes that had a low iron status to begin with, but iron supplementation may be warranted in athletes that fit this description. A physician should be consulted if iron supplements are considered to ensure that iron intake is kept at appropriate levels.